Question 22.47 says, using a Stork-enamine synthesis, show how you might accomplish the following transformation. So we're just going to look at part A, where we take acetophenone and we make this 1,5-dicarbonyl compound. So to me, the dead giveaway that we're dealing with the Stork-enamine synthesis, even if the question hadn't mentioned it and just said, how would you make this compound? Well, the fact that you're dealing with a 1,5-dicarbonyl compound is usually a dead giveaway that you're dealing with a Stork-enamine synthesis. So how are we going to do this? And what we talked about in class at the end of lecture on Friday is that when you take a ketone like acetophenone and you treat that with a strong base, the problem is that that enolate that you form is not stable enough to act as a Michael donor. And we looked at our table of Michael donors and what's an appropriate Michael donor. So obviously just a simple ketone is not an appropriate Michael donor, but what Gilbert Stork developed is he said, well, what if we take this and we just treat this with dimethylamine and H+, and we learned this back in chapter 20. And if we remove water, what do we generate then? Well, we'd have ourselves an enamine in this case. So we have an enamine. And the thing about the enamine is that it is more stable and it is less nucleophilic and less reactive, and therefore it will react at the beta position of an alpha-beta unsaturated ketone. So if you remember from chapter 20, this is how we make an enamine. So now that we have an enamine, you can see that if you draw the resonance structure of an enamine so that you have a negative charge, so if we take this pair of electrons here, we put them down here, and we draw this, if you draw the resonance structure here, you can actually see how it's less reactive than just the enolate of the ketone. You can see here that you have a doubly charged species. So you do have a negative charge on your carbon, which is nucleophilic, and some electrons ready to attack something there. But the thing is that the overall charge of the molecule is neutral. So the first step of the synthesis would be to generate an enamine. So now that you have an enamine, you have an appropriate Michael donor. And now you need to figure out what your Michael acceptor is going to be. And you can see that in your Michael donor, so let's just take a look at the nuts and bolts of what we've got here with this molecule here, just ignore the curved arrows. You can see that you have 1, 2 carbons in this molecule, and you have 1, 2 carbons in your final molecule. So the molecule that you're going to use for your alpha-beta unsaturated ketone is going to have carbons 3, 4, and 5. And if you think about it, if you look at that and you think retrosynthetically, you can say, okay, well, let me just draw this out. Let me draw this ketone out. You could say, okay, I'm going to have this, and all I have to do is put a double bond here, and then I have a Michael acceptor. So this is a perfectly acceptable Michael acceptor. So now I have my Michael donor. I know what my Michael donor is going to be over here. Michael donor. So my Michael donor is going to be my enamine, and my Michael acceptor is going to be this alpha-beta unsaturated ketone. So I'll just put alpha-beta unsaturated K, big K for ketone. All right. So what's our next step going to be? Okay, so to write this out properly, now that we have all of our pieces in place, the way we would do this is we'd say, okay, well, we're going to start with acetophenone. We're starting with acetophenone. And the first step is to make that enamine. So we're going to say dimethylamine. We need catalytic acid. And overall, we are removing water to form our enamine. So now we have our amine. And the next thing we're going to use is we're going to have our Michael acceptor. So here's our Michael acceptor, our alpha-beta unsaturated ketone. And when you're doing a enamine, Gilbert Stork enamine synthesis, and we talked about the mechanism of this reaction in class. We looked at the nuts and bolts of it. And basically, in the end, after you've reacted your enamine with your Michael acceptor, you end up with a doubly charged species. And you can find more information about that on if you look at page 1084 in Klein, he goes into detail about the doubly charged species that contains an iminium ion and an enolate ion. And then when you treat it with aqueous acid, what you do is you hydrolyze your iminium back to a ketone, and you convert the enolate into an enol, which tautomerizes to give your ketone. So you end up with your final product like this. So you have 1, 2, 3, 4, 5, your 1,5-dicarbonyl, and that's all there is to it. That's how you do the storic enamine synthesis. And I think this is a really important reaction to look over when you're studying. It kind of incorporates something from chapter 20 and something that we learned in this chapter as well. Storic enamine synthesis.